Last week, in the past 2 weeks, we have been looking at the properties of tensors. And so in that, we have looked at several things. First of all, we explained that the properties of tensors are built on the definition of tensor. The properties are built on the foundation of the definition of what a second order tensor is. That is a linear transformation of a vector into another vector. And when you operate it on a vector, the result is a vector. So that is what it is. And then that transformation must be linear. If it transforms a vector to a vector and it doesn't transform it linearly, then it is not a tensor. So you only know a tensor by what it does to a vector. There are also things that look like vectors, but because of their non-linearity, they are not tensors. So all the properties of tensors derive from the way they behave, and that is the definition. We also went and gave examples of what tensors are. These 9 examples are just some specific examples of simple tensors. The identity, which does nothing. That means that the vector, it does nothing in the sense that the vector you put in is also the vector you get out. So, but it's still a vector. Since you get a vector out, and after you are putting a vector, even though the two are the same, it still satisfies technically the definition of, so the identity is a tensor because you give it a vector, it gives you back a vector. Even though the two are the same, it's still a tensor. The spherical tensor, which multiplies the vector, which gives you another vector by scaling it, is still a vector, is still a tensor. The coordinate transformation, which gives you your vector in a new set of coordinates, is still a tensor. The projection, the shadow, which is what the sun does to any vector, it's also a vector because it transforms in a way that is linear. And but we have a mathematical format for it, which is what you see as a projection tensor here. The vector cross, which does a similar thing like what you know from vector analysis, is a tensor. When you take the vector cross itself, you can look at it as a tensor, and the vector right hand side is now what it is operating on. So the vector cross is a vector with the cross products put together constitutes a tensor. The dyad is the operation that takes two vectors and then the tensor product. If you now operate that thing on a vector, it will give you a vector. It is in the case of the dyad, it is the combination of A circle times B that is the tensor. So if you now operate that quantity on a vector, it's going to give you a vector. The annihilator tensor is the zero tensor, because if you operate it on any vector, it will give you the zero vector, and it is a tensor in its own right. There are many others, but these are, and you can see that in each case, we're able to show that the definition works. That is, it will transform a vector to a vector and do the transformation linearly. We went through to explain that, and we established the fact that the properties of tensors that we are concerned about are based or rooted on the way they operate on and on the way they operate on vectors. So that is the foundation of it. If you have any difficulty with what a tensor is, you go back to the definition, and then you see that that definition is valid. So don't worry about anything. Your base is the definition of that is based on the way it works with vectors. So that is the foundation. Then we establish issues of what equality means. Again, Equality in tensors is if two tensors are equal, then that means that when you give them the same vector, they are going to transform to similar results, to results that are identical. If you can find anything otherwise, then those tensors are not equal. We also talked about what happens when you multiply a tensor by a scalar. We define the issue of inverse for invertible tensors. And then we showed that if tensor y is the inverse of tensor t, then tensor t is also the inverse of tensor y. So the reverse is true. From that, we also went into checking whether the inverse of a tensor is really a tensor. Then we defined the tensor basis. We defined the tensor basis. And we showed that the tensor basis, just like vector basis is 3, the tensor basis is 9. There are 9 objects in the tensor basis. And then we can now find the components in the basis. We established a rule for finding the vector and the scalar components of the basis. We're able to find the scalar components of the basis. And then, so we now went to the examples we had before. Those 9 examples, we found their components. And the annihilator we showed so that the components are 9 zeros. And the identity, we saw that the components are 6 zeros off diagonal and unity on the diagonal. For the dyad, we saw that the 9 components are UI, Vj. If U1, U2, and U3, V1, V2, and V3 are the components of the vectors, by just taking all the possible combinations, which are 9, you get all the components of the dyad that are related to it. So that's very simple, very simple. So we can find the, we also looked at the fact that products, when we are talking about scalars, there is only one definition of product. So when you say take a product of 2 scalars, so that's only one meaning. But with vectors, we define the scalar product, and with scalar multiplication, scalar product, vector product, and tensor product. There are at least 4 different meanings you can attribute to the word product when you are dealing with vectors. When you are dealing with tensors, the things become far more complicated. There can be up to 30 different meanings. But of those 30 different meanings, we are dealing with only one in this course. We may deal with others later on, but the composition is the only product that we are handling here of tensor. But we just want it to be very clear that even though we are dealing with only one, there are so many others that might be useful later on. But you can appreciate the complication. That is, when you are talking of a 0-order tensor, we have only one definition of product. When you are talking of a 1st-order tensor, we are talking about 4 different interpretations. Therefore, there's a need to disambiguate. So you cannot come and say, okay, take the product of these 2 vectors. Then somebody will have to ask, which one are you talking about? Which one you did? The product means many things. So while it is okay to say take the product of these 2 scalars, you cannot say the same thing on the vector without becoming ambiguous. So there is a need to disambiguate when you are dealing with vectors. It is far more so when you are dealing with tensors of the 2nd order. By the time you get to the tensor of 3rd order and 4th order, you are in a complete state of Babel. It's complete confusion. So we have to therefore tread carefully and say exactly what do we mean when we are talking of product. So we would not just be talking of product, we will give them names. That's why when we are talking of the 2nd order tensor, we talk of composition. So we define composition specifically. It's composition, and we do what we mean by it. When we bring other products, we are going to call them by their names. We are not just going to talk of product glibly like that. So here we talk about the composition, okay, composition, and then we talk about the composition of dyad bases, and we showed the very simple rule. When you have a chain of dyads and you are doing the composition of all of them, you will explain that you don't need to worry. You just do the tensor product of the first and the last vectors in the chain. And then all the near vectors take their dot products. Once you do that, you have gotten the answer. And that means that dyads are so easy for us to deal with. Dyads are now what play the role of your base vectors in your vector analysis. That role is played by dyads. So anytime you are in trouble in vector analysis, you run to your bases. IJK, when you were in secondary school and first and second years. Now E1, E2, E3, when you got to third year, you are looking at E1, E2, E3. These things make very, very easy, make life easy for us when we are dealing with vectors. Similarly, when we are dealing with tensors, we are going to work with dyads every time we have problems. It will give us more things to work on, but the arithmetic becomes very simple. So that who doesn't like simple things? So then we introduce the idea of the transpose. We introduce the idea of the transpose, and we say that give any two non-trivial vectors, if you have this expression that was circled here, if you have this expression, then vector T is the transpose of vector S. If this equality holds true for any two non-trivial vectors, you just reverse the order of operation, and if you still get the same answer. And then once one tensor is in a transposal relationship with another, we use the same symbol to represent both of them and just put a raised T for the other. So the transpose of S will be S transpose. Because they are so similar, there is no need to use a new symbol to represent them. So, and then we also show that the transpose of a dyad is simply a reversal of the constituent vectors. Then that transpose, the idea of transpose creates the idea of symmetry. A tensor indistinguishable from its transpose is said to be symmetrical. So when there is no difference between a tensor and its transpose, that particular tensor is said to be symmetrical. Now, we did a tentative introduction of the idea of cofactor last 2 weeks. Today, we are going to go bold. We are going to tell you what a cofactor really is. And we are going to define a cofactor in the way that it makes sense to an engineer. That is something a mathematician is not particularly interested in, because our foray into tensor analysis is utilitarian. Believe me, even though you seem to be doing a lot of theory, you will see that everything we are talking about tensors is for utilitarian practical engineering goal. And today we are going to take a first step to see that we are not just interested in theory. Our theoretical interest is rooted in very, very deep practical issues. And the cofactor is what explains it nicely. When you take any mathematical text, the cofactor looks so abstract. And I don't blame you if you quickly run away from the part of the book that is talking about cofactors, like I used to do. A cofactor is actually a very interesting thing. I will explain the cofactor to you today in a way that should be more appetizing than what you will read in most textbooks. I owe this to a very deeply engineering text. That book by what's the name of the book? I have the book here. That's a book by Gottin and two other authors. You are the first people to bring the idea of cofactor to me in a way that is appetizing. You know, if you people are lucky, you are lucky you came to the world when things are very good for children. When people like us came to the world, we were at the point when our mothers would feed us with pap. And when you feed a little child with pap, the child is likely to hate it because it is a bit sour and the child is spitting it out. I don't know how many of you have seen village women who will block the nose of the child and force the pap into the child's stomach. And the child will be yelling throughout, but as the child opens the mouth, some of the pap sometimes the child can even faint in the process. Whereas in your own case, maybe your parents added sugar and added milk and you just enjoyed yourself. That idea of adding milk and sugar to make the pap more appetizing was not known to our parents. Or if it was known, they couldn't afford it. So they just forced the pap down our throats. But for you, yeah, somebody gave you milk and gave you sugar and you made it appetizing. So I'm going to offer you milk and sugar to make the idea of the cofactor much more appetizing. And I hope when I've added the milk and sugar, you will now see why you need to know about the cofactor of a tensor, and it will no longer be something that you are forced to look at. It is something that you actually find enjoyable, and you can see where it is going. And I hope I therefore make it appetizing. So this definition you see on this page is not the fundamental definition. We're going to give you a more fundamental definition, and then we will derive this definition from it and any other thing. And the fact that the second principal invariant is simply the trace of this will become obvious once you have the fundamental understanding of what a cofactor really is. And like I said, I can tell you that the most important topic in today's class will be the third thing we will do, which is the cofactor of a tensor, which will be fully introduced. Okay, so we introduced in the last 2 weeks the scalar functions of tensors. After we looked at the scalar function of vectors, we threaded gently, and we introduced the scalar invariants, which are the scalar functions of tensors. The three of them are the first, second, and third invariants. And the first invariant, we call it the trace of the tensor. The second one is the trace of its cofactor. And the third one is the determinant of the tensor. I'm going to ask you a question shortly on this page. I will bring this page back later, and I'm going to ask you a question on it. And we explained that the trace itself, that this first invariant is a linear operation, but the other two are not linear. So the trace of a dyad is simply remove the tensor product and replace it with a scalar product. That is how you get a trace. If you want to get a trace of a dyad, just remove the tensor product inside it and replace it with the trace of a cofactor. Is a little bit more involving, as you can see. But it has, when we work it out, it comes to something like this. In many textbooks, this expression here is used to define the trace of a cofactor, but it doesn't define it. It's just derived from, once you define the cofactor properly, you can get this, as we shall show if we get that far today. The determinant of a tensor is the third principal invariant, and we can find it in component form here. Then we talked about some linearity issues, and then I think the last thing we talked about was the fact that the product of the determinant of a composition is the product of the two tensors. If you have a composition AB and you take the determinant, you might as well take the determinant of each one of them and multiply to get the determinant of the composition. And this page constitutes a proof of that idea. And then we introduce the idea of the inner product of two tensors, and it is the trace of the composition of the transpose of one with the composition of the transpose of the one and the other one. It doesn't matter which one we take the transpose of. You can take the transpose of the first one or the second one. And because the composition is commutative, it doesn't matter which one you take as the first or the second one. Just take the transpose of one of them. If you don't take the transpose of one of them, what you have is not an inner product between the two of them, but the inner product between one and the transpose of the other one. So if you want to get the inner product of two tensors, you must take the transpose of one with the other one before you carry out the composition and taking the trace of that composition. So the above, the scalar product of tensor n on the dyad basis is given by this, and it is the same thing as the component. This makes it look like your vector analysis. You know, if you want to know the component of a vector on, say, E1, you just take the dot product of that vector and E1. That gives you the component. If you want to know the component on E2, just take the dot product, the scalar product with E2. Similarly, if you want to know the component of a tensor on any of the dyad bases, just take the inner product of that tensor with that particular base, and that is it. So this is a very good thing because it makes your knowledge of tensor and vector analysis transferable to tensor analysis. So that is the beautiful thing about this. So don't forget it. So that is just a short, quick run on what we did last week. And so let me just take that one off and then come to today's lecture. Come to today's lecture. Let me come to today's lecture and say this slideshow from the beginning. So in today's lecture, we are going to do more of the properties of tensors. We're going to go further. And before I go on, I want to ask a question. And I want you to go to the chat room. First, there are two questions. What is the difference when I put this triple equality and when I put this other equality? That's the first question. I want to see how many people can distinguish between that. Why do I sometimes use 3 equality, which is the identity, and sometimes I use I just say equal. What do those things mean? I want to see whether whether you really know, whether it's just a style, or does it really have fundamental meaning? What do you understand? So you go to the chat room and respond to me. Please remember, class, that your responses during the chats and all those things are part of the things that you earn grades on. So it is still, if you have not been responding to the chats, and we take a record of all the chats in every class. And so if some people earn as much as 10 points in their final assessment because of that. Some people earn 0. So, and remember, class, I don't add marks to students. Where you will get free marks is all this talking in class. So if you have 39%, you are going to fail. You are going to get the 39%. I'm not going to add 1 mark. That's very wicked. I know, I'm very wicked. But what happens is that I have given you an opportunity to get free marks. If you don't take that opportunity, you can say I'm wicked here, but then you know you are dealing with a wicked man. You need to have a way to survive him. So if you are the person that is refusing to survive me, I am not saying that your responses in the chat must be correct. I'm just saying you must make an effort. And I give you grades. I give you marks for making the effort. Okay, so let me read what I have seen. Okay, triple equality is a strict equal. It doesn't mean a strict equality. It means a definition. It means equivalent. It means identical. It means that's the identity. That's the definition. It's not equivalency. It means identity. Okay, so the triple one means identity. That is the first here in the first case. Thanks class for that viral. I like that kind of discussion. When I ask you questions, I want to see response, because your responses motivate me to know what to emphasize and what your weaknesses are and how to help you. So when I say this is identical, I mean this is the definition. This thing here is what we mean by the first principal invariant. Any other thing you will get are just, any other things you get are just equivalencies. But this is the meaning. This is the fundamental meaning. Okay, so this is the fundamental meaning of the second principal invariant. This is the fundamental meaning of the third principal invariant. So the second question I'm going to pose is harder. triple requires all the components are equal, while double requires the components to only triple requires all. No, the answer is that when we use the triple equality, which is the identity, we mean that is the definition. That's the fundamental meaning. The other one is just showing that it is equal, but it's not the definition. Okay, so it is equal. It is you can replace it, but it's not the fundamental definition. Okay, so that's, at least we've settled that one. So let us go to the next question. The next question is that I want to put it to you that the second equality is here. In two cases, it should be an identity, actually. In two cases, it should be an identity. In one case, it is just equal. So I want you to find them. So is it 1 and 2, or 1 and 3, or 2 and 3, or what? So let me put the question again. Okay, let me type the question so that you will understand. So is it 1 and 2, or 1 and 3, or 2 and 3? So I want to see what your answers are. Somebody says 1 and 3. 1 and 3. 1 and 3. 1 and 3. Joe Ashalu says 1 and 3. 1 and 3. Ah, everybody is saying 1 and 3. Nobody disagrees. Somebody say, Ginika Olua, Precious Michael and Ginika Olua are the first two people that are wrong. Olua Pelumi is also wrong. Okay, let me see more wrong people. Christian Nkega is also wrong. Okay. Okay. Mike Emmanuel Oni has joined the right people. So, okay, so I will, so it's good. 1 and 2. Precious Michael, you are wrong. Okay, so it's good that we have these responses. Now, 1, this should be let me actually do it. So let me actually do it now, so that so I am saying here that this is actually the correct expression. That is the trace of T. This is the definition of the trace. Similarly, this is the definition of the determinant of a tensor. But this is not the definition of the trace of a tensor, of the tensor T cofactor. Now, so since we have settled that, I want to ask a last question, which is more difficult than the previous two. Now, tell me, what is the definition of the trace of the cofactor? We want to do the trace of the cofactor. We want it to be triple. What do we do? I will open a page, and do I do a page? No, if I do it, you will be seeing me. I want to see whether anybody will get it right in the class. I want to see whether anybody. Suppose we want it to be triple. What would be on the middle side here? What would be defined as the trace of TC? What would be the definition of the trace of TC? Of the cofactor? Anybody? I just make your attempt. Don't worry if you are right or not, because I'm going to tell you the right thing shortly. So I just want you to try. Just want you to think. I just want your mind to be active in class. Okay, let me do it for you, and you will see, why. You will say you will beat yourself when I tell you the right answer, because you will just be saying, it should be obvious. It ought to be obvious. Okay, if we are looking at the definition of the trace of the cofactor, if we are looking at the definition of the trace of the cofactor, not just an equality, this is it. This is the definition of the trace of the cofactor. But the other one we saw before is equal. That is, we can prove that the two are the same, but this is the original definition. You can now derive the other one from this. But this is the fundamental definition of the trace of the cofactor. You can show that the two are equal, but this is not, that the other one is not the definition. This is the definition. So if you wanted to make it a triple, this is it. But if you don't want to make it a triple, that other one is okay. So I think, okay, let me see what comments are still in the chat. Okay, so at least I've answered the question now. So let us move on. It is expected that you should have read up on the notes and slides from last week. I will not ordinarily repeat them in this week's lecture. I have done that, but there are two issues that can be, okay. I've gone through all the things that we are discussing here. I've run through the inner product, the product of determinants and all those things. So let us see, what are we covering today? What we are covering, what I have on the menu today are 5 things. To show first of all that members of a tensor is a member of a Euclidean vector space. We've been saying that vectors are first order tensors. The other side of the coin is that all tensors of all orders are actually members of a particular vector space. So on the one hand, you say that a vector is first order tensor. On the other hand, you say that even first order, second order, third order, fifth order, all of them can be shown to be members of vector spaces. But you have to define a vector space in the way we did in week 5. Because I didn't teach week 5 slides directly, I am thinking that many of you may not have done sufficient work on that. So I am leaving out the first point here. I will postpone it till later when I've gone to that. But I can leave it out because it's too much of a theoretical nature, and I'm not interested. Today, I want to work on very, very practical things. I will leave that theory. Not that the theory is not good or useful, but most engineers don't have the patience for things that don't have immediate application. So we will look at numbers 2, 3, 4, and 5. If we can cover 2 and 3 today, we have done well. So even though my goal is to look at 2, 3, 4, and 5, but if I can cover 2 and 3, I would think today is well done. So in continuation of our closer examination of the properties of tensors, we shall cover some of these properties. The mathematics may look cumbersome. The strategy is simple. Focus on definitions and principles. All that will be left is repeated application of simple rules. The math is not as difficult as you think. The math is just cumbersome and can be sometimes tedious, but it's not difficult. It is for you to retain what the definitions and principles are. If you know those things, you will see that after some time, just working a lot of examples will make you an expert in this thing. Not only will you get your A, I want everybody in this class to aim at getting an A in this course. It will be my delight to give everybody A. But provided you yourself will know that you deserve an A. I don't want to dash you an A, but I want you to know that I am teaching this course in such a way that you can get an A and know the course and actually be proud that you got an A in it, that the subject matter is what you not only know, you can teach other people. That is what is possible. It is possible if you listen attentively in class, if you go through the book. I gave you a book. I hope you still have access to the book that I wrote on this topic. And I also gave you nearly 500, at least, I think in this first chapter there are at least 100 fully worked examples. If you go through all those worked examples and you practice your continuous assessment in the mask, I don't see what is stopping you from getting an A. I don't see it. So, but if you deserve an F, I will oblige you, no problem. But that's not my desire. Just tell you. So this will be complicated only when you don't practice. You will surprise yourself on what you will know at the end. You will be, when you look back as to what you have learned and what you have known, the things that look difficult before, you will be surprised. So there's no reason why you cannot get an A in this course. So can just add, even if you have never got an A before in your life, this may be your first A, if you are like that. And if you have been getting A's, this should just be an additional one. Okay, so let us move on. In the same way as vectors. Okay. Before I even say that, I want to ask a question. Can you square a vector? If you can, what will you get? If you can't, explain. Go back to the chat room. Can you square a vector? Can you square a vector? If you can, what do you get? Can you square a vector? Can you square a vector? Somebody says you can't. Kamal says you can't. Any other question? Any other attempt? Any contrary opinion? Can you square a vector? Yes. Okay. You can square it. What you will get if you square it? Is it a vector you will get? Anigbo said no. Israel, you have. Yeah, you can. Tani Tolorun. Squaring means multiplication by itself, but multiplication is ambiguous. Okay. Yes, you will get a vector. Precious, you are wrong. You can square, but you will not get a vector. Yes, you can. You get a scalar. Okay. Okay. Let me tell you. True, as somebody said. Let me see who said it. Ogochukwu Uba. Ogochukwu, you are right. That squaring means multiplication by itself, but multiplication is ambiguous. But squaring a vector is not ambiguous. Squaring a vector is to take a dot product of the vector with itself. When you say square a vector, you are referring to the dot product of the vector with itself. The square of a vector is the inner product, the scalar product, the dot product of the vector with itself, and it gives you a scalar. And that scalar is the square of the magnitude of that vector. And you take the square root of that to get the magnitude of that vector. That is in the mathematical parlance. That is how you square a vector. A vector can be squared. So squaring vector v is v dot v. V dot v can also be written as v squared. That is a common nomenclature. So you can square a vector. And what you get is the scalar, which is the square of the magnitude of the vector. You can square a vector. You can also square a tensor. If you square a tensor, it is the inner product of the tensor with itself. And the square root of that is the magnitude of that tensor. So you can square a vector, you can square a tensor. If you square a vector, you get the square of the, so the square of a vector is the scalar product of the vector with itself. The square of a tensor is the scalar product of the tensor with itself. So, inspired by the fact that the scalar product of T with itself is a scalar, we define the magnitude of the tensor as the square root of that product, just like in vectors. But remember, in the case of a tensor, it is the double dot that is the squaring it, because you are taking, remember, okay, I want to make a statement now. I want to make a statement now, and I want you to tell me whether the statement is correct or wrong. This T double dot T is the composition of T with itself, right or wrong? T double dot T is the composition of T with itself, right or wrong? Just say right or wrong. T double dot T is the composition of T with itself, correct or wrong? Please go to the chat room, and I've made a statement. Is that statement correct? Oluwapelumi says it's right. Boluwatife says it's right. Christian Ikenga says it's right. And they are all completely wrong. Precious, you are wrong. And I've already told you are wrong. Now, the next thing, allow you, tell me what is the correct thing. If it is wrong, tell me what's the correct thing. The inner product of, or the scalar product of a tensor with itself is the composition of the tensor with itself. You say it is wrong. Why is it wrong? What's the correct thing? It is the composition of the tensor with its transpose. It is not the composition of the tensor with itself. It is the composition of the tensor with its, is the trace of the composition of the tensor with itself. It is the trace of the composition of the tensor with itself. That's what I was explaining before. So you can see how easy it is for you to forget. Is it clear now? Let me see whether I have it in this slide, set of slides. See, S double dot T is the trace of ST with T, not the trace of S of the composition of S with T, but the trace of the transpose of S with T. You can easily forget this. So just bear this in mind. So you can see how easily you forget. Is the class clear on it now? You can see why most of you were wrong. I want a response. Can you see? Is it clear now that okay, so Balala can see, okay, so you can see. So the inner product of T, the inner product of T, the magnitude of T, or the T double dot T, is the trace of the composition of T with its transpose. Similarly, we can say that the angle between two tensors can be computed from theta is equal to the cosine, the angle whose cosine is S dot T over the magnitude of S, magnitude of T, which are defined here. Unlike vectors, these values do not have the familiar geometric interpretation of directed lines and included angles. The algebra trumps the geometry. Do not attempt to visualize a geometrical interpretation for a tensor magnitude. It doesn't exist. So because unlike vectors, where a vector is defined by something with magnitude and direction, a tensor is not defined by its magnitude and direction. So you cannot represent a tensor by a directed line element. A tensor is far more complicated than that. So you do not therefore have that very beautiful geometrical interpretation that has been etched in your mind since you were in secondary school. This is the bus stop of that interpretation. It does not apply to second order tensors, but you can still define magnitude and direction, but it is no longer the same geometric interpretation that you had before. So there is somebody commenting. Okay, so the next thing we will do, the next thing we'll do before we go on break, let us talk about decomposing tensors. Remember that we decompose vectors every day, every time. You decompose vectors into their I, J, and K components. You have a single vector and you make 3 vectors out of it. Why do you do that? You do that because it is easier for you to deal with those 3 vectors than to deal with the single vector. Once you have I, J, and K components, getting a dot product, getting vector, getting everything becomes so easy. Even getting the magnitude is easy. You just know that square of each, if you square and add all the components and take the square root, so many things. So decomposing, but you can decompose vectors essentially. Well, essentially, it's the only one way to decompose vectors. Just break them into their I, J, and K components. We break vectors into components in only one way. Tensor can be usefully broken down in several different ways. Some of these decompositions are, like the component form, additive. When you look at the vectors, the decomposition of vectors is an additive decomposition. Additive decompositions can also happen in tensors. There are 4 different additive decompositions. You can break a tensor into its skew and symmetric forms. You can break it into the spherical and deviatoric forms, or you can break it into its spectral form. And all of these things are additive, including breaking it into its dyads, into its dyad basis. So there are 4 ways you can break a tensor into, you can decompose a tensor additively. So when you decompose a vector additively, the tensor is equal to all of those things added together. Then there is an important multiplicative decomposition. I don't know there are other multiplicative decomposition, but there is an important multiplicative decomposition we call the polar decomposition. You will get that in the next course of continuum mechanics. That is critically important. But so there are at least 5 different ways you can break a tensor down into simpler forms. Decomposing tensors, component form, that's the weighted sum of dyads that add up to the tensor. Components are the weights. This turns the tensor into a weighted sum of up to 9 dyad bases. 3 additive decompositions are possible: skew and symmetric parts, the spherical and deviatoric parts, and spectral form of eigenbases. The multiplicative decomposition, rotation and stretches in polar decomposition. So those are the 5 different ways you can break a tensor into forms. Let us look at the first one. We already know how to break a tensor into dyads. Because all you do is just get the components of the 9 components of the dyad, finish. So that's it. We've been doing that already. But if you want to break a tensor into 2 spherical and deviatoric parts, every tensor can be decomposed into spherical and deviatoric parts. A spherical part of a tensor is obtained by dividing its trace by 3 and using the result to scale an identity tensor. So you take the trace of the tensor, you divide it by 3, and you use, because when you take the trace, you know it's a scalar that you get, and you use that to scale an identity tensor. You get this form here. That is the spherical part of the tensor. So every tensor can have this as the spherical part, because just take the trace, divide it by 3, and multiply it by the identity tensor. That gives you the spherical part of the tensor, and the spherical part of the tensor is written as SPHS, so spherical part of tensor S. Now, the deviatoric part is what remains after removing the spherical part. So if you take the tensor itself and you subtract the spherical part, the remnant is called the deviatoric part. It should be obvious that if you add the deviatoric part and the spherical part, you recover S, just because of the definition. The definition of the deviatoric part gives it out, because if you transfer this to the other side, it would now be the spherical part for the deviatoric part is equal to the tensor itself. So this is idiot proof. This is clear. So this is 1. This is number 2. Because the first one is breaking it into its dyad basis, which we've already done. Now, if you now try to take the trace of the spherical part, if you try to take the trace of the spherical part, you will see that since this is a scalar, 3 trace S is a scalar, you take it out, just take the trace of the identity tensor. The trace of the identity tensor is 3. So that 3 will cancel the 1/3 there. And so the trace of the spherical part is simply the trace of the tensor itself. The trace of the deviatoric part is 0. So a deviatoric tensor is a traceless tensor because it has 0 trace. So if you try to take the trace of it, if I tell you a tensor is deviatoric, what's the trace? The trace is 0. A deviatoric tensor has a 0 trace, but it's not all traceless tensors are deviatoric. So you say every deviatoric tensor is traceless, but not all traceless tensors are deviatoric. It's traceless because it has 0 trace. You will see other tensors that have 0 trace and are not deviatoric. So that is the second additive decomposition. You could also break a tensor into its skew and symmetric parts. We can decompose a tensor S into symmetrical and antisymmetric parts. The antisymmetric part is also called the skew tensor. It's defined as that which is negative of its transpose. To get the symmetric part sim S is just the average of the tensor plus its transpose. So if you do the average of its tensor and its transpose, you get the symmetric part. Now, the skew part is this difference, is half of the difference between the tensor and its transpose. You can easily see by adding these two equations that if you add the symmetric part and the skew part, you are going to recover the tensor itself. It is easy to see from these expressions. So, the transpose of the symmetric part, if a tensor is symmetric, its transpose will be the same. So, but the transpose part is negative of the transpose of the skew part is negative of the skew part. So, the transpose of a sum is equal to the sum of transposes. That is a proof that is taken here with a proof. Okay. You can also get these things from the component method. So you can, all these things, you can use the component method. So every time you can prove a theorem or a result without going back into components, it is sweeter, it is nicer. But if you are in trouble and you don't know what to do, you can break things into components and it may be easier for you to do. So this is a component way of expressing the symmetric and the antisymmetric part. You could also do the same for the deviatoric. Traces of skew and symmetric parts. You will see that the trace of the skew part is also 0, just like a deviatoric tensor. But the trace of the symmetric part is the same thing as the trace of the tensor itself. So whether it is the spherical part or the symmetric part, the trace is the trace of the original tensor. No judgment can be made on the symmetry or skewness of a deviatoric tensor. However, its symmetry wholly depends on the original tensor from which the deviatoric part is taken. If the letter is symmetric, so will the deviatoric part. If it is skewed, so also will be the deviatoric part. It is quite possible for a deviatoric tensor to be neither symmetric nor skewed. So a deviatoric tensor may not be symmetric or skewed. Well, I want us to take a 20 minutes break and come back at noon. noon is when we are returning from break, noon. From that point, we are going to spend that remaining half on the cofactor of a tensor.